subatomic particles. So we've learned that the atom is not a solid indestructible thing, but it is composed of smaller particles. Those are known as subatomic because they're smaller than atoms. And the three that we care about in chemistry are protons, neutrons, and electrons. Particle physicists will tell you about a whole bunch of other ones. There's muons and bosons and all kinds of things. That's physics. The mass of a proton and the mass of a neutron are extremely similar. They differ in the fourth digit. The mass of an electron is significantly smaller. Real world analogy, if the proton was the mass of a baseball, the electron would be the mass of a grain of rice. So weighs a lot less. That unit, kilograms, is not a great unit to express these types of masses. It's ideal to have a unit that's roughly the size of what you're measuring. And even the smallest of the metric prefixes is not going to be good enough. So they made up another unit to use for masses of small particles like this. And that sounds like, oh, they made up a unit. Where did all units come from? They're made up, right? You know, a foot used to be the length of the king's foot. And then, you know, if the next king has a bigger or smaller foot, chaos? I don't know. But this unit is called the atomic mass unit. It's a unit used for measuring the mass of an atom. So the definition is kind of weird. One AMU is defined as 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So this carbon atom in its nucleus has 6 plus 6, 12 of these particles, right? And then there's the electrons that really are basically nothing. So if we take this mass of these 12 things and divide it by 12, that's an AMU. So the result is that the mass of a proton or a neutron is very, very close to 1 atomic mass unit. And for I think everything we do in Chem 1A, we can just say that it's 1. So here are some things you do need to know. The charge of the proton and the electron are equal in size, in magnitude, but they're opposite in sign. So if you put a proton and an electron, did I say neutron? I hope not. The proton and the electron. If you put a proton and electron together, overall they have no charge. The neutron is neutral, it has no charge. So we need to know the names of these particles, proton, neutron, electron. We do not need to know these masses in kilograms. You might need to look it up for a problem, but that's about it. And the masses in AMUs, you see how close those are? For most of the time, we can just say that the proton and the neutron are each 1 atomic mass unit, and the electron is 0. Of course, it isn't 0, but it's, for all intents and purposes, 0. And then the charges. These are the relative charges. That's all we care about. We don't actually care about how they were measured in coulombs. So we say the proton has a +1 charge, and the electron is a -1, and the neutron has 0 charge. So matter's generally charged neutral because the protons and electrons are present in equal numbers. But you can get imbalances, and one of those happens during an electrical storm. So you get a buildup of positive charges and negative charges that are separated by space. And that's not a stable situation, and so that will resolve kind of violently by a lightning bolt. Static electric shocks also happen this way. So the number of protons is very important. That's what identifies a given atom as belonging to a certain kind of element. So that's like the soul, the personhood or the personality, the protons. That's who you are. You can't change who you are. You can change what you look like, right? We do that all the time. I mean, you can put on a gorilla costume. There's all kinds of things you can do. But does that change who you are? No, it doesn't. So the number of protons is called the atomic number, and is given the symbol Z, which doesn't seem to make sense, but this came from the German word Zahl, meaning number. So this was number. It's kind of like N, right? Except it was in German. So if we look at helium, all helium atoms have 2 protons. All carbon atoms have 6 protons. That's what makes it an atom of carbon. The atomic number is on the periodic table for all the elements. So here, looking at this individual square, that whole number at the top, that's the atomic number, the number of protons that an atom has. Here's the chemical symbol and its name. So each element has its own unique atomic number and its own unique chemical symbol. Right? So when we look at this periodic table, this one has names on it. The one you get for an exam, the one on the wall, they don't have names on because we need that space for other things. But none of these boxes have the same symbol. Those chemical symbols are 1 or 2 letter abbreviations. That first letter is always capitalized. The second letter, if there is one, is never capitalized. So helium has the symbol He, carbon has the symbol C. These kind of make sense. That's the first 2 letters of helium. It can't just be H because hydrogen got there first. Hydrogen is H. So then we have to go to a second letter to make it different. So why do some of them seem so weird? Like, why is Na the symbol for sodium? There's no N's or A's in the word sodium. Well, sodium was discovered a long, long time ago when people still used Latin, and the Latin name for it was natrium, because it came from the ocean.
Why don't we just keep natrium?
Why don't we just keep natrium? That's a great question. It is a great question. I don't know the answer to that one. So that's where the Na comes from. So all of the ones that seem wonky, like tungsten has the symbol W. What's up with that? It's wolfram. Lead, Lead, is Pb. Plumum, Plumbum. That's where the word plumbing comes from, because they used to use lead pipes. They found out later, not a good idea. So many things we did that weren't good. Yeah, I'm going crazy too.
I wonder what they're going to find in the future.
Yeah, what are they going to find in the future? I don't know if I want to think about that.
Yeah, same.
They're probably going to find out that Diet Dr. Pepper is like super, super toxic.
I think they already found that.
Well, I'm still alive. Anyway, getting back to isotopes. So all the atoms of a given element have the same number of protons. So in that way, they are the same. They all have the same number of electrons as atoms, because those have to match up with the protons. But some of them have a different number of neutrons. And so this is where Dalton's atomic theory, where he said they were all identical, we have to modify it because they differ in the number of neutrons. So atoms of the same element that have different numbers of same number of protons, different numbers of neutrons, are called isotopes. So using neon as an example, all neon atoms have 10 protons, but some of them have 10 neutrons, some have 11, and some have 12 neutrons. This is not information you can find on the periodic table. This is not information that you would be expected to remember. They studied it, and they found out, right? Some elements only have one kind. Some have 3 or 4. There's not really any nice pattern behind that. And so for neon, with these 3 different isotopes, you might think, well, a third of it has 10 and a third has no. You have to determine the relative amounts for each element, And those are generally expressed as a percentage, which is referred to as the natural abundance. And we'll get back to that in a minute. So we can't just say Ne to distinguish these three different isotopes. So we need something a little more detailed. We talk about a mass number. That has the symbol A. I will not try to trick you with the Z's and the A because I think they're dumb. But atomic number, number of protons, mass number, number of massive particles. So it's the sum of the protons and the neutrons. And so we can symbolize isotopes like this. We can use the chemical symbol for the element. We put their atomic number, the number of protons, down here, and the mass number up there. So these are representations of the three different isotopes of neon. I remember having a hard time remembering, does the 10 go on the bottom or on the top? So what helped me is I realized, how do we find the number of neutrons? We take the mass number and subtract the protons. So it's like these are stacked up just to make it easy for us. So this is the number of neutrons in each of these. So that's one way to indicate different isotopes. Another common notation is to use the element symbol or the element name followed by the mass number. Because do we really need the atomic number in that? If we want to know what the atomic number is, we have a periodic table. You always have a periodic table. So these could be called neon 20, neon 21, and neon 22. So here we have the breakdown. Here's the symbols. They all have the same number of protons. They have different numbers of neutrons, so their mass numbers are different. And the natural abundance is just what it is. So neon 20 is 90.48% of all the neon. There's very little neon 21, and not so much neon 22, 9.25%. These are not numbers that you're expected to know. So we should be able to do things like this. What are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? Okay, so what is the atomic number? It's the number of protons, right? And where do we get that? From the periodic table. So I put a little periodic table here on the slide for us. So there's carbon. How many protons does carbon have? 6. So the atomic number is 6. And then it asks for the mass number. The mass number is the sum of the protons and the neutrons. Well, they told us that this one has 7. So the mass number will be the atomic number, the number of protons, plus the number of neutrons. So 13. And the symbol. So we could write the nuclear symbol where the mass number is a superscript on the left and the atomic number is a subscript on the left. Or we could call this C13, or we could call this carbon 13. Here's another one. How many protons and neutrons are present in an atom of potassium 39? Well, how do we figure out the number of protons? It's actually the small number at the bottom, 19. Oh, yeah, it is the big number on the chart here. So there's two ways. You can look at this. The 19 tells us it's 19 protons. Or we can find this on the periodic table where it is the big number on top. So 19 protons. How many neutrons? 39 minus 19 is 20. Now, if you're doing that for points, use your calculator. Right? It's easy to just, I don't know. So any questions about that?
Why did they put the mass number instead of just the neutron number?
That's a good question. Why do they put the mass number instead of the number of neutrons? The only thing I can think of is that the mass number will be very close to the atomic mass of that atom in atomic mass units. So a carbon-13 atom, because it's 13 total protons and neutrons, is going to have a mass very close to 13 atomic mass units. It's the only thing I can think of right now.
I was also curious about why they would repeat the number of protons. It's kind of.
I know. Why put the 6 down here? I don't know.
Because if it wasn't 6, it wouldn't be carbon either.
It's possible. No, they didn't know about this before we had the periodic table. I don't know. I think it's a bit redundant.
We need to wake them up and ask.
Yeah.
To make you write extra numbers.
Well, and what we'll see as we go through the class is that chemists don't like to write extra things, and the number 1 we just leave out a lot. So then, why do we put this in? That's an excellent question, and I do not know. So the electrons are like in this cloud around the nucleus. The electrons are kind of like the clothing of the atom. So you have a person, you are who you are, and then you've got your outward appearance. You can change your outward appearance. So an atom can change its number of electrons. It can lose electrons or it can gain electrons, but the number of protons stays the same. So what happens when you gain or lose electrons? Well, now you're going to have a charged atom, and charged atoms are called ions. If it has a positive charge, it's a cation. If it's a negative charge, it's an anion. And we need to remember those. So cations are positive. Paul. Yeah. Cations are positive, anions are negative. And to indicate that we have an ion, we're going to show the charge on the right side of the element symbol. You will always see the sign, plus or minus. Here, these each are +1 and -1, and so we didn't write the 1 because it's not absolutely necessary. And I think that also helps to avoid, we don't want that charge to look like an exponent. So if we have more than 1, like if we have calcium 2+, we write the plus after the 2, or oxygen 2-. We don't want this to look like the variable oxygen to the -2 power, if that helps you remember it. And I think that's it for today.